We're going to take a look at chapter 8, I think. Yeah. Bonding, general concepts. And this is going to be our traditional review. You may have noticed that this was a pretty short review document. This out of character for me. I had split it into two different documents because I thought the solutions to the problems. Come here. The solutions to the problems took a little more extra effort. So I reduced the number of problems. Trying to give you some duplication in there so you get experience and hopefully get bored doing them. Remember? Curiosity and boredom, your two best friends. Okay, so let's take a look at number 1. And in the beginning, there are a lot of highlighted ones. The force between two bodies having identical electrical charges. Is there a force between two bodies with identical electrical charges? Should be repulsion, correct? They have two positives or two negatives. They're going to be pushing away from each other. So let's see, is that one of our choices? Is a force of repulsion? Yeah. A's it. Right? Like I always say, if there are no oddballs in there, like 2 of the above and none of the above, once you find the right answer, you're done. So A is the correct answer for 1. Now, what if I made a slight change and you're reading too fast? Right? The force between two bodies having different electric charges should be a force of attraction, shouldn't it? Well, that's not one of your choices here. So I have to change that too. Okay, how about number 2? Atoms having equal or nearly equal electronegativities are expected to form what? Well, if they have equal electronegativities, in terms of what we studied this semester, where did they come from on the periodic table? They'll be nonmetals. Right, nonmetals. We haven't studied the metallic bond. Right? That we're saving that one sort of until second semester. So those equal negativities of metals are not going to produce the same result as nonmetals. Nonmetals that have nearly equal electronegativities are not only going to produce covalent bonds, but they're going to produce non-polar covalent bonds. A perfect example is just that simple compound. The equal pull of electrons either direction, it's got to be non-polar, no other choice. Oh, so the answer should be C. Non-polar covalent bond. All right. Oops, I'm turning it on first. There we go. Come on. It's not behaving. Whoa. I was just starting to like this thing. There you go, it stabs me in the back. Number 3. For the elements cesium, fluorine, that's not correct. That's carbon sulfide. Cesium, chlorine, and fluorine. Okay, for those three, the order of increasing electronegativity. Increasing electronegativity is what? Lower left, upper right. So we know that this has to be the greatest electronegativity. Upper right-hand corner. In fact, on the Pauling scale, it's 4.0. There's nothing higher. So fluorine is the greatest. What's next? Well, if you got a triplet, I like to bracket. So that's the most, what's the least? Cesium's way down here. So that means chlorine has to be in the middle. And if you look at the periodic table, that fits. Chlorine is below fluorine. That was a pretty easy one, actually. How about 4? The electron pair in carbon-fluorine bond could be considered. Okay, look at our choices. Closer to carbon, closer to fluorine, closer to carbon. Okay. So the question is actually asking us which one has the stronger pull. The higher electronegativity should put the partial charge toward fluorine. Like that. Okay. Now we can probably answer the question. All right, closer to carbon. No, throw that one out. I mean, that first part of the statement disqualifies A. Closer to fluorine, okay. How about the rest of the statement? Because fluorine has a higher electronegativity than carbon. Yeah, B is true. Let's see, we got some oddballs in there. Closer to carbon, no. Inadequate model. Yeah.
I was going to see if there's any first generation students in the classroom.
No.
Okay.
I'm second generation. We got some second generations in here.
Oh,
Probably a lot. Oh. Too bad I'm not a natural born liar. Okay, so B apparently is the only one of those choices that fits. Five. Which of the following molecules has no dipole moment? So we got 3 to choose from, and we can say all of them have no dipole moment or none of them have. So we've got to take a look at each one. Carbon dioxide and ammonia and water. Now, if you remember our work with these molecules in the past, you won't have to go to all this trouble and draw them out. But if you do the Lewis dot structure for carbon dioxide, you're going to find that's your molecule, Lewis dot structure, which means the VSEPR says that you have 2 groups and no free electrons. So it's got to be linear. 2 groups means linear. That means this dipole moment and this dipole moment cancel each other out. So that's nonpolar. How about this one? In other words, it has no dipole moment. That's what that means. This one, if we draw the Lewis dot structure, we're going to find that it has 3 bonds plus a lone pair. Okay. So that means tetrahedral, electronic structure. But if we cover up the lone pair, what do we have? We have a trigonal pyramid. Right? So the trigonal pyramid says that way. This one has a dipole moment. How about water? We've done water so often, we all have that one memorized. Right? That has a dipole moment. So, which of the following has no dipole moment? Just that one. 8. Did I go too fast? Okay.
Can you review what a dipole moment is again?
Yeah, dipole moment is the word that expresses the unbalance of charges. In physics, a moment is a reference to momentum, mass times velocity. But we sort of stole that from them and brought it over to chemistry. Used it to indicate what might be considered a force if a molecule is suspended between two plates, negative and positive, then it would feel a force as it orients itself negative toward the positive plate and positive toward the negative plate. It would feel a force pulling it in one direction or the other. And that is an expression of the dipole moment, that force. And it's due to the difference in electron distribution in the molecule. In other words, if the electrons tend to spend more of their time actually closer to one side of the molecule than the other, then that makes a slight negative charge on one side and a slight positive on the other. Okay, was that too complicated? I was sort of rambling there for a while too. Yeah. All right. How many I can get here? Oh, yes, now I got 3. Okay. 6. Which of the following has the smallest radius? Okay. So the best way to approach this one is to start with the neutral atoms. Potassium, chlorine, rubidium, sulfur, and argon. And look at their position on the periodic table. What's the trend? Right? They get smaller from lower left to upper right. Okay. Smaller. Lower left to upper right. So if that's the case, then chlorine is, well, argon is in the upper right. So we would put the smallest one would be argon, the next one would be chlorine, and the others, potassium's bigger. We've done that one, we've done that one. Sulfur's to the left, so sulfur would be over here. And rubidium is below potassium, so it would be the biggest one. Potassium here. Okay, that would be for the neutral atoms. Excuse me. But now we're talking about charges. So if we charge them, we make this one 2 minus, this one a 1 plus, oops, and this one a 1 minus. That was neutral, of course. And rubidium should be a 1 plus. Okay, now we have to ask ourselves, what has happened to the neutral atoms? Well, in this one, we've added 2 electrons. And this one, and actually, hold on a second. There's a better approach to this. Except for this one. These, potassium, argon, sulfur, and chlorine, these are all isoelectronic. Okay. Those are all isoelectronic. And rubidium actually has the next principal quantum number level. So it's going to be bigger no matter what you do to it. Right? So we can say, if we're going for the smallest one, we can count rubidium out because it's in period 5. And these are in 3s and 4s. But they're isoelectronic. Okay. So if they're isoelectronic, that means they still have different numbers of protons, right? Argon is 18, 17, 16, and potassium is 19. 19. So look at what's happening. We've established the electronic structure is all the same for these. And that means that based on argon, it should be 1, 2, 3, 3s2, 3p6. They're all the same. Isoelectronic structure. Okay. Did I lose you yet? Okay. You understand why I got rid of this one? Because it's a higher N number. Right? So it has to be bigger than them no matter what we do to it. Okay. Now that these are isoelectronic, we look at the number of protons. Okay. So we got the same number of electrons, but we got 19 protons there. That's a higher effective nuclear charge than any of the others, pulling on the same number of electrons. So that means this one has to be the smallest. And you can verify it with real data. It's true. Okay. Did I lose anybody? Okay. I was starting to bark up the wrong tree, and I said, there's an easier way to do this. And that was it. Which of the following arrangements is in order of decreasing size? Okay, now we're dealing with, let's see, we have the same, I got the cursor on the way. Okay. We got gallium, calcium. I'm scanning all of our selections to see if they've got the same, calcium, potassium, chlorine, and sulfur. Okay, so we know that we've got gallium 3+, we've got calcium 2+, potassium 1+, chlorine 1-, and sulfur 2-. Now let's see if these guys are related in any way. Gallium 3+, that's going to be a sticking point right there. I was looking to see if they were all like argon. Calcium is like argon. Isoelectronic with argon. Potassium is argon. Chlorine is argon. And sulfur is argon. Okay. So it should be fairly easy to put these in order, like we did before. But then we're going to have to say, what do we do with gallium? Okay, we'll put it in decreasing order. Let's see, are those in decreasing order? Yeah. Bigger, the way the carrots turn. That's good. Okay, so these should be in what order? If they're isoelectronic, then we look at 20, 19, chlorine is 17, sulfur is 16. If these are isoelectronic, then the smallest one should be this one, right? That should be the smallest one. Okay. And the next one should be potassium. And the next one should be chlorine. The next one should be sulfur. Okay, now we got to figure out what to do with gallium. Gallium is 31. Here's why gallium is the biggest one. Even though it's got more protons, it also has a complete 3D. It's got a complete 3D. And that's going to balloon. Whereas these others don't have any 3D electrons. Does that make any sense? I hope it does. That's the best I can do. So that means gallium is going to be the biggest one. And the rest of them are in that order. Oops. No, I'm sorry. I went the wrong direction, didn't I? Hold on a second. Saying gallium is the smallest one. Why does not the 3D? Okay, it's in the same principal quantum level. Three Ds do penetrate some. I don't have a good explanation for that other than this right here. Because it's got 11 more protons than the rest of them. That must be the reason that gallium is the smallest. So if I ask you for an explanation, that's the best you can do because that's the best I can do. If you can come up with a better explanation, I'll open. That's what makes sense to me. I thought at first that the 3Ds would balloon, but they're still in the third principal quantum level. All right, let's take number 8. In the reaction between magnesium and sulfur, the magnesium atoms, magnesium atoms become what? Anions, cations, polyatomics, share electrons, or crystallize. This is a metal. This is a nonmetal. So the electrons are going to transfer like that. And when you end up with that as your compound, this has to be that. So it becomes a cation. It loses electrons. You can go by rule of thumb too, or by the magnesium is an alkaline earth, right? And they're always 2+. As long as you've got a metal combined with a nonmetal, then it behaves that way. Now, if you got sulfur combining with another nonmetal, that's a different story. Okay, let's see. I'm only going to do number 9 on this one. Choose the molecule with the strongest bond. All right, this one, the reason I picked this one out is it's somewhat counterintuitive. These are all based upon halogens, diatomic halogens. Right? That's one of the first things we learned when we were learning the elements, if these are at 1 atmosphere pressure and room temperature, they're always diatomic. Right? So that if a word problem comes up and says you react chlorine to something else, you know to write it Cl2. But now we're talking about the bond that holds them together, and they're all single bonds. So we don't have to deal with the comparison of doubles, triples, single bonds. You can prove that to yourself with Lewis dot structure. How many valence electrons do they all have? 7. So that means they share 1 electron from each, and that makes the octet. Right? So this would have 7, one of them's in here, this would have 7, one of them's in there to make the bond. So each one of them, they're all single bonds. So now we need to compare try to rationalize the strength of the bond. They're all sharing electrons. So what affects the strength of the bond? The overlap, right? They're different orbitals. In other words, fluorine is working with 2p orbitals. This is N equals 2, 3, 4, 5. So what that means is the atoms are moving farther apart, and the overlap is not as complete. So you get, this is the weakest one. This is stronger. This is stronger. And here's the anomaly. You would expect that one to be stronger because they're closer together. The problem is they're so close together that now you're getting proton-proton rejection. Okay, the nuclei are pushing out against them because they're so close. Okay, so this is the strongest one of the group. And data proves it. We're just rationalizing it. Why is it that way? Okay. All right. That's the one. Let's see if it works. Let's see. Let's pick up. I need that much right there. That stuff above 12 is essential for the problem. Draw the Lewis dot structures of the molecules below and use them to answer the following questions. These molecules have a 0 net dipole moment. Which one of those have a 0 net dipole moment? All right. So let's take them one at a time. And of course, I'm going to run out of time as usual. We drew this one in class, boron trihydride. Remember why we drew that one? Because it had a deficient octet. Boron is 5 electrons. And then 3 times 1 is 3, so we have 8. If we draw boron, like that, like that, like that, 2, 4, 6, oops, excuse me. Doesn't have 3 valence electrons, excuse me. I'm getting where I am. So now it's a 2, 4, 6. And the EPR theory says if you got 3, what's the structure? Trigonal planar. So all the dipole moments, whatever they happen to be, will cancel each other out because they're all either directed in or directed out. So you don't even have to know if it goes this way or that way. They're all equivalent dipole moments. It's probably this way. Remember what I said about determining the dipole moment of a molecule? You got to know 2 things. Right? The dipole of the bonds. Right? Do you have dipolar bonds? And what's the geometry? So that was nonpolar. How about this one? NO2. NO2. So oxygen has 6, which is 2 times 6 is 12. And then nitrogen has 5. Yeah, 5. So 5 and 12 is 17. 17 electrons. So we have nitrogen in the middle. We have an oxygen and an oxygen. So that's 2, 4, 13. So we start at the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. This one's an oddball. An unpaired electron means this is a free radical. And it's very reactive. But that doesn't have a bearing on answering the question. We have 3 groups, which means trigonal planar electronic structure. So we're going to have like this, 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 and that. And the dipole moment, oxygen should be like that, which means even with that extra electron up there, you're still going to have a slight dipole that way. So this one is polar. How about SF6? Right? Sulfur is 6 valence electrons. Fluorine is 6 times 7 is 42, plus 6 is 48. So we have sulfur, 1, 2, 3, 4, 5, 6 fluorines. Okay. So that's 2, 4, 6, 8, 10, 12. We have 36 left over. So what 2, 4, 6. 6 times 6 is 36. That uses up all our electrons. But if we put 6 around each fluorine now. So what does VSEPR say about 6 groups? It's octahedral. Right? And each one of these bonds is polar toward the fluorine, but they're all pointed in, well, you can only have opposites with 2. But wherever you've got a pair, you got an opposite. And they cancel each other out. So this one is non-polar. All right. So that's Roman numeral 1 and 3. I need to erase some of this. And then 4 is ozone. Right? So 3 times 6 is 18, correct? So that's 2, 4 equals 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. We used up all our electrons. This is 1, 2, 3 groups around the central atom, means trigonal planar. So it's going to be like this. Right, with the electrons around those oxygens. And these bonds would be nonpolar, correct? Right, those bonds are nonpolar. So what we're saying is that if these bonds are nonpolar, the molecule can't be polar. Except I'm wondering about those 3 electrons up there. But we've got 6 over there and 6 over there. That's why I'm going to call it nonpolar. Even though, now if we had none of these extra electrons over here, then that pair right there might go that way. But under the circumstances, we'll call it nonpolar. One more. Wait a minute, that's not right. that pair does make a difference. 2, 4, 6. Oh, wait a minute. 2, 4, 6, 8, 10, 12, 14, 16, 18. Is that right? 3 times 6 is 18. Oh, no. I'm not finished. What did I do wrong? Somebody tell me. I didn't complete the octet on the central oxygen. Right? These guys have octets, but that one doesn't. So what we've got to do is go like that. Now we've got this. This one still only has 2 pair. This one has 3. Okay. Now we can look at it logically. We would not expect a dipole moment anywhere in here, except that these two balance that side, and this one is all by itself. So ozone is slightly polar due to that lone pair. Okay, we got the last one, PCl5. Oops. Read my question. 0 net dipole. Okay, so if that's polar, then it doesn't fit. So we've still only got 1 and 3. Let's look at the last one. You're going to keep me getting confused. PCl5. Okay. Phosphorus has 5. How do I know it has 5 valence electrons? Count from the left. 1, 2, 3, 4, 5. Over. Phosphorus has 5 valence electrons. 7 for each one of these, so it's 35 and 5 is 40. So phosphorus and chlorines all around. 2, 4, 6, 8, 10. So now we've got 30 left. Right? 6 around each one. 6 times 5 is 30. Use them all up. That means we have no lone pairs. All right, so 5 means what shape? A trigonal bipyramid. Remember the one like this, like that, with phosphorus in the middle, got a chlorine here, chlorine here, chlorine here, and then we go chlorine there, chlorine there. So they all balance one another. And even though the dipole is probably towards chlorine in each case, they all cancel each other out. So this one's nonpolar also. So there's our 3. I can feel I'm moving code back after lab. All right. I think I picked this one. 13. Not just for the application to this chapter, but also because it uses, this is an organic compound, and we haven't studied organics. So I'm going to try to help you with some conventions. Eventually, you'll see them again if you go on to organic somewhere. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure whose skeleton is? All right, in this case, this is fairly simple. Right, you got 4 carbons. And those numbers just mean this is carbon number 1, 2, 3, 4. That's misleading. It doesn't mean that there are one carbon there and two carbons. Okay. And then we've got, I'm going to use that as a bond. And then we got 1, 2 there, oxygen there. Okay, what is that asking? How many electrons must be shunned? I mean, add up all the valence electrons. First step in your Lewis dot structure. Just add up all the valence electrons. So we've got 1, 2, 3, 4, 5, 6 hydrogens. 1, 2, 3, 4 carbons. 4 times 4. And we got 1 oxygen. 6, 6. Okay, so we got 16 plus 12 is 28. So that's D. Now, if you see this written out in shorthand, so to speak, these hydrogens would be like that. This hydrogen would be like that. This one would be like that. And this one would be like CHO, like that. That's what it would condense to. And the point is that these hydrogens belong to that carbon, not to this one. And this one belongs to that one, that one belongs to that one, and these two belong to that one. Carbon rules, as organic chemists would say. Okay, that was 13. And that's 16. In the Lewis structure of ICl2 minus, how many lone pairs of electrons are around the central iodine atom? So they tell you which one is central. You don't even have to figure that one out. Iodine's in the middle. So how many electrons do we have to deal with here? We've got 7 for iodine and 7 for each chlorine. So 3 times 7 is 21, right? But we got that extra one. So we actually have 22 electrons to deal with. Okay, now we've got chlorines here, chlorines there. So that's 2, 4 is 18. 2, 4, 6, 8, 10, 12. 12 is 6. We got 6 electrons left over. Okay, so how many lone pairs of electrons are around the central atom? These are all filled up. So all 6 have to go around iodine. 6, we have 3 lone pairs. 6 electrons, 3 lone pairs. So don't get messed up with wording. It says how many electrons, lone electrons, but they're paired. So that's why the answer is 3. And of course, the answer should include, I mean, if you think you're looking for 6 and it's not there, back up and say, what do they mean? 3 lone pairs. One thing I forgot to do with that one, brackets with a charge. That would be the proper Lewis dot structure for that one. Let's see, I'm going to get over here. What's 20? Let's see. Yeah, 20. Which of the following types of molecules always has a dipole moment? Okay, so we got to look at each one. Linear molecules with 2 identical bonds. Right? If they're linear and have 2 identical bonds, they have to cancel each other out, correct? Okay, so this is nonpolar. We're looking for the one that always has a dipole moment, right? So it can't be that one. Tetrahedral molecules with 4 identical bonds, equally spaced. Like carbon tetrachloride, methane. They're nonpolar. trigonal pyramid molecule. Trigonal pyramid. So what does a trigonal pyramid look like? Well, it's got one here, and it's got one in the back, and it's got one out here, and it's got one out here, and it forms that trigonal base. How did it get that way? That's not normally the way you would see a distribution of bonded electrons. The only way it can get that way is if it's got a lone pair up there. And our example is ammonia. This one is always polar. Oh, we found our answer. Trigonal planar with three identicals, they all cancel each other out. Boron for a hydride example. So C has to be the answer here. That one is always polar. And the reason is that lone pair. (21) Which set contains atoms listed in order increasing electronegativity? All right, so they're kind of messed up here. Increasing electronegativity. Well, you can look at A. Fluorine is the least electronegative of that group. It can't be. There's nothing more electronegative than fluorine. So that one's false. How about phosphorus, nitrogen, oxygen, and fluorine? Phosphorus, okay. Look where phosphorus is. Look where nitrogen is. Right, so it's more electronegative. Oxygen is more, then fluorine's more. That's good. That one is true. We have any oddballs in there? No, we found our answer. Okay. So that went up to the right, up to the right. (22) Which choice has the bonds listed in the order of increasing bond energy? Okay. E says all the same. So we're probably going to have to look at each one. So what are the bond energies of these guys? This is more electronegative than that one, and that one's more electronegative than that one. So the bond energy should be highest for this one. And they're closer together. The hydrogen is closer to the fluorine than this one, and then that one. It should be the other way around. So that was false. How about B? Oh, this one's a no-brainer. That's no-brainer. Yep. Triple bonds, everything else being equal. This triple's stronger than that double, stronger than that single. That's true. What about the next one? All right. This one goes back to the one we already covered, where we had bromine. This one should be the strongest of all. And then it would be this one and that one. So that was false. They're out of order. How about D? We disqualify this one first. This bond, C2H4, should be this one, like that. Right, you can draw out the Lewis dot structure and you prove it to yourself. And then this one Right. So this one has to be stronger than that one. If it's talking about this double bond versus that triple bond, there's no contest. The triple is stronger. So that's turned around backwards. All right, so that one's false. All right, so they're not all the same. B is the only one that's right. Yes.
On your study guide, it has like on the right answer it's C's. On ours, it has O's. So I'm not sure if it's like a typo.
Oh, this one?
Yeah, like on B for the little paper that you gave us, it says C.
This one?
Yeah.
Hold on a second. Yeah. Okay. It's a similar argument. Right. That should have had carbons there instead of O's. But you can say the same thing for that. Right. Triple's bigger than is more stronger than double, stronger than single. Yeah. Let me make a note of it. 1, 2. It should be C, C, C. Maybe I'll just leave it there and see if the next class catches it. Oh, 22, we're done. 20, 23. In the gaseous phase, which of the following diatomic molecules will be the most polar? Okay. Why do we want it in the gaseous phase? Generally speaking, if you put something in the gas phase, then you've already got it to a point where there are no other energy influences. Right? It takes energy to get it from a solid to a liquid to a gas. And now once it's in the gas phase, those molecules are free. They're independent from one another. And any measurements you make on them are supposedly for the molecule itself, rather than for any interactions that it might have with its neighbors. Okay, so back to the question. Which of the following would be most polar? All right, let's see. CSF, CSCl, NaCl, F, and Li. Okay. What you want to look for here is there's separation on the periodic table, because you're not given numbers. Right? If we were given numbers, we could just do a subtraction and compare the values, the differences in electronegativities. But we're not given that, so we have to look at their separation on the periodic chart. All right, which one? Lithium and fluorine would have a fairly polar bond. Sodium would have less so because it's below lithium. Okay. So this one's more polar than that one. How about sodium chloride? Well, chlorine is below fluorine, so it'd be less electronegative. So we're still sodium chloride. How about cesium chloride? Well, cesium chloride puts them further apart than sodium and fluorine. So now we're looking at this one. But now you compare fluorine and chlorine. This is more electronegative than chlorine. There's your answer. Okay, process of elimination. Or you got a periodic table in front of you. You can look, say, which one is the furthest apart, and you can go straight to cesium fluoride. Can't go far enough. Let's back up. Back 1.5. 1.6. 1.6. Which of the following ionic compounds has the largest lattice energy? The lattice energy most favorable to a stable lattice. Okay. Lattice energy, remember, lattice energy is you take the gas of the cation and the gas of the anion, and they come together and make a solid like that. That's the expression for lattice energy. When they come together, they're very exothermic. Extremely exothermic. So you want the one that gives you the greatest amount of energy from that process. So if we look at each one of them, barium and, let's see, barium would be 2+, oxygen would be 2-, beryllium would be 2+, and oxygen again is 2-, and cesium would be 1+, and iodine would be 1-, and sodium would be 1+, and bromine would be 1-, and then barium would be 2+, and sulfur would be 2-. Now, what's the influence here? Two things. Coulomb's law, right? How much energy is actually expended in separating those charges, and then the distance between them, and that's Coulomb's law too. Right? Remember that one? E equals whatever Coulomb's constant is, and then the charge on one of them and the charge on the second one divided by R, distance between them. So the greater the charge, the higher the energy. So we would see 2+, 2- together would be the best candidates to start with. Okay, so we're going to eliminate this one and this one because they're only single charges. Now, which ones could get the closest together when they come together? Oops. Yeah, that's right. Well, sulfur is below oxygen, so it's a bigger ion. That means you can't get as close with the cation. So it's a battle between these two. So now, since oxygen's the same for these, the anion is the same. How about the cations? Which one's the smaller one? Look where they are on the periodic table. Beryllium is way up here. Barium is way down here. Beryllium is the smaller ion. So it's going to have the closer approach, the higher energy. Okay? That's why B is the answer to this problem. There's a lot of stuff to cram in your brain for one test. It's tough. And the older your brain gets, the worse it is. 26. The first electron affinity value for oxygen is, let's see, our choice is unfavorable, favorable. And the second electron affinity value is unfavorable, favorable. So the first electron affinity value for oxygen. So what would that be? Oxygen gas, remember the formula? Plus an electron yield. That's the first electron affinity. Okay, second electron affinity. Right? Yeah, second electron affinity. Take that one. Second electron. Okay. So we're also given hints. Unfavorable is endothermic. That means you have to put energy in to get it happen. So this is a non-metal. Nonmetals generally are attracted to electrons. Right? But this is the neutral ion, atom attracting an electron. This should be exothermic or favorable. Right? This is a negative delta H. This is favorable. But notice what you got going here. For your second one, you've got a negative trying to come close to another negative. That's a problem. There's a repulsive force in there. This is unfavorable. So that's why the answer is D. Favorable, unfavorable. Now, I hope you're thinking about oxygen when it's in an ionic compound is 2- charge. So it has to get this. How does it do it? Well, it's the balance. Right? Does the favorable exceed the unfavorable? Right? Do you get a whole lot of energy out of this one that can overcome that one? And I think the answer is yes. This is unfavorable, but not as unfavorable as this one is favorable in the reaction. And you end up with a 2- charge almost. All right. 10 minutes still. 27. Using the following reaction data, calculate the energy of an HF bond. Okay, this looks to me like it's going to be a Hess's law. So what are we looking for with an HF bond? I think I'm right. I want to be sure I'm not barking up the wrong tree because that'd just be wasting our time. Okay, so our target equation for the HF bond, we want to form this. But remember, we want to exclude all other influences. So this HF bond has to be a gas formed from gases. That's how you measure the energy of your bond. Right? It's going to be exothermic, right? Because these, when they come together, they're going to give off energy. They're more stable here than they are there. So in order to do that, we have to say, right, what can we use? Right, there's HF is the first equation, but we only need half of it. Right? So we can say H2. I want to do several steps at once. Oops, excuse me, H2, yeah. Yields HF gas, and this will be, it's in the same order, so it's a negative sign. And it's going to be half of that, 266. 71. 271, right? Twice that is 542. Yeah. Okay, so that takes care of this one. Now we need to do these right here. See, this is gas also. We need 2 hydrogens on this side. Actually, 1 hydrogen on this side. And this one. Yes. So we need 1 hydrogen, let's see, 1/2 of this one, and 1 of those. So now we need to flip the sign and take half of it. So it's 216, so 432. Yep. And then the same thing for fluorine, right? Fluorine, 1/2 of F2. And this is gas. Okay, so we had to flip that one and take half of it. So we got to flip the sign. See, not 154, it's 77. Negative 77. Did I lose anybody yet? Because I'm doing several things at once. So we've got this one here, 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 here. This one cancels that one, and this one cancels that one. So we got these two here, that one there. Now all we have to do is add them together. Right, they're all negative, so I can say 13, 14, 1, 8, 9, 16, and 1 and 4 is 5. Minus 564. That's the enthalpy of the reaction, and the energy of the bond is 564 kilojoules. That's how much energy you would have to put in here. You get that much out when you do the reaction, but in order to break the bond, it's always in those terms. You got to put that much energy in to break the bond, 564 kilojoules per mole. Okay. That took up a lot of time, didn't it? 28. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? All right. Well, in the interest of time, CH3OH is methanol. That's good. We don't even have to write the structure. CH2O is formaldehyde. That's good. CH3O. Okay. We're going to do this one because it's the answer and we're short on time. Okay, so this is 4, this is 3 valence electrons. This is 6. So that's 9, 13 electrons. Okay, so we have carbon in the middle. We have 1, 2, 3, 4, 5. So there's an oxygen. Oh, excuse me. Start over again. Carbon. 1, 2, 3 hydrogens. And 1 oxygen. Okay, so 2, 4, 6, 8. And that's 5 electrons left over. Okay, 1, 2, 3, 4, 5. I guess it's possible, but it wouldn't be a stable. The key there is a stable. This would not be a stable molecule because it's a free radical. And D is acetylene, right? Same stuff you find in a torch. And the last one, C3H4 is, let's see, CH4. And I was trying to do it too fast. This would be 3 times 4 is 12, 4 is 16. So we have C, 4 hydrogens. There we go. 2, 4, 6, 8, 10, 12. 4. So we got 1, 2, 3, 4. Now we can move. This has got an octet, that's got an octet. This is only, it's only got 4. So we can move this one over here and this one over here. Now we have that's a stable. That's a valid Lewis dot structure. I was getting lost myself. I probably lost you too. My mistake was trying to do it quick at first. I should have just gone with the rules and done the whole thing the way it should be. Let me see if the next one can be done quickly. Otherwise, we'll break for the lab. Now, I better come back to this one after lab. Let's finish this review. Number 29. Using the following electron negativity values, select from the following group of molecules that fits the given statement. Okay, so we got these selection of molecules, CH3CHO, CO2, CH3Cl, C2H6. This molecule contains a carbon atom with trigonal planar geometry. Right. So, which one is it? The first one is CH3CHO. Okay. Now, notice that one of the answers is none of these. So, if we find one that does have trigonal planar geometry in its makeup, then we can stop because we found an answer that is not none of these. So, how about this one? All right. So, we got 4 valence electrons here. We got 3 times 1 there. We got 4 here. We got 1 there. And oxygen has 6. So, that's 7, 11, 14, 18. 18 electrons. Right? So, remember what I mentioned earlier about the way these compounds are written in organic chemistry. These hydrogens belong to that carbon, and this carbon is linked to that carbon. So we would write it this way, right? And then we would put these 3 hydrogens here, and then we'd have 1 hydrogen here, and we have oxygen there. Okay, so we got 1, 2, 3, 4 hydrogens, 2 carbons, 1 oxygen. Okay, everybody's there. 2, 4, 6, 8, 10, 12. So that's 6 electrons. So now we start from the outside and work our way in. Right? 6 electrons. Right? So they're all used up. Hydrogens are all happy. This carbon's got an octet. This carbon has 2, 4, 6. It needs an octet. So the best way to do that is to take one of these pair and make a double bond there, right there. Okay? So that means that pair is used. And now we have the Lewis dot structure for this molecule. Okay, so around this carbon, we've got 4 groups. VSEPR says that 4 is a tetrahedron. Right, so this one is tetrahedron right here. This one has 1, 2, 3. This one is trigonal planar. There's your answer. That's the one with trigonal planar. All right, 29. Let's scroll down. And let's see how many of these we can get on here. Oops. And we're going to have to just take 2 at a time. How about that? 34. Of the following, which molecule has the largest bond angle? Okay. So we've got to do the structures. Ozone, we did ozone before. Okay. Ozone had this, and that. like that. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now let's see. 3 times 6 for oxygen is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we're covered. Now, largest bond angle. Remember, bond angles have to have a central atom and 2 attached atoms. Right? So the bond angle would be between here and here, with this at the apex. So what would this structure be? Right? 1, 2, 3 would be trigonal planar. Right? You can't have bond angles with lone pair electrons. Right? So this is the only bond angle in that molecule right here. Right? Trigonal planar says this, that. Right? So, and bond angles in trigonal planar would be 120 degrees, approximately. Okay? So, for this one, it's 120 degrees, is the bond angle. For B, OF2, this is 7 times 2 is 14 plus 6 is 20. 20 electrons, O in the middle. Yeah, 2, 4, 16. So that's 6, 6, 12. Minus 12 equals 4 electrons. There we go. Okay. Around this central, and they all have octets, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. They all have octets. What's the structure here? Tetrahedral. And remember, the bond angle in a tetrahedral is 109.5 degrees. All right. So let's do this. And let's put this up here so we can get them all on the board at the same time. (109.5 degrees). Now, that's with a perfect tetrahedron. But remember what I said about when the tetrahedron has lone pair electrons in it, they tend to balloon out and they shrink that value. Right? So we'll save that until the end when we start comparing them and have to make a decision. HCN. We did this one in class before. Right, this is linear, 180 degrees. And water. We've done water so much, we ought to be able to do it in our sleep. (109.5). Okay. If we need to break a tie, then we'll consider the lone pair electrons. But we're not going to have to break a tie in this one because this linear says the bond angle, right? The bond angle is here. Bond angle's here. Bond angle's here. Bond angle's here. This bond angle, since it's linear, is 180 degrees. That is the largest angle of all of those compounds. So C is the answer. (35). Which of the following molecules is nonpolar overall? All right. So we have SF4. Let's see if I can spread them out so I can do them all at once. SF2, C, CCl4, D, H2S, and E, OCl2. Okay. Sulfur has 6, same as oxygen. Fluorine has 7, so 4 times 7 is 28. And 28 plus 6 is 34. 34 electrons. Okay, we have sulfur here. We have fluorine, 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 fluorine. Okay, 2, 4, 6, 8 minus 8 is 26. Okay, all octets, we have 4 times 6 is 24. These 2 electrons. Okay. Now, what's the structure of this one with 5 groups? VSEPR says this is trigonal bipyramid. Okay, so that means what? We've got a trigonal base with sulfur in the middle, and we've got something up here and something down here. So where does that lone pair go? Remember, in trigonal bipyramidal, when you have one lone pair, it goes on the triangle. So that means this is a fluorine, that's a fluorine, this is a fluorine, and that's a fluorine. Okay. And fluorine is more electronegative than anything. So it goes this way, it goes this way, and it goes this way. They're not all balanced. They pull away from it, which makes this a polar molecule. Right. So it can't be A. How about SF2? I'm going to have to erase this. SF2. So we have 6, and 2 times 7 is 14, so there are 20 electrons. S, F, F. So that's 2, 4, minus 4 is 16. So that's 12 more. 4, like that, like that, like that, like that. Okay. So around the sulfur, you've got 4 groups, which means tetrahedral. And tetrahedral would be like, let's see, up here. All right, so 2 of these fluorines are going to be here, maybe one back here in the back, and then the other lone pairs are going to be here at the apex. So the bond is here and here. That's a bent molecule. So this one's going to be polar also, right? The dipoles do not cancel. So this is polar. Carbon tetrachloride. So you have 4 here, and 7 times 4 is 28, plus 4 is 32. 32 electrons. Carbon, fluorine, 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 fluorine. Now, all of these bonds, the bonds, individual bonds are polar. Right? We just kind of skipped over that, but all of the bonds in these molecules are polar. There's a significant difference between the electronegativities. So the bonds are polar. Now we're focusing on the geometry. All right, so that's 2, 4, 6, 8. Minus 8 is 24. Okay, everybody has an octet. So that's 6 electrons times 4 is 24. All used up. This molecule is a tetrahedron. It has 4 groups around the central atom. And every bond is exactly the same. Dipole moment. That means they all cancel each other out. This molecule is non-polar. All right. Well, we found our nonpolar molecule. H2S is like water. It's polar. OCl2 should have O in the middle, Cl here, Cl here. Let's see. 6 plus 14 is 20. So 2, 4, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This one is a bent molecule too. 4 groups, tetrahedron, molecular structure is bent. So this one is also polar. This is the only nonpolar in that group, carbon tetrachloride. All right, let's see. I think the next one is, yeah, designated also. Let's just move it up so we can see it better. 36. Which of the following molecules are nonlinear? All right, nonlinear. NO2 minus. All right, that's 5 here, and 2 times 6 is 12 plus 1 for that charge. So that's equal to 18 electrons. All right, let's see. Put our bonds in. O, 2, 4, 14, 2, 4, 6, 8, 10, 12. Equals 2. So 2 of them have to go here. Okay. This molecule has octets for the oxygen, but not for the nitrogen. So we need to make a double bond. If we make a double bond with that pair, it won't help nitrogen at all. We've got to pull a pair from one side or the other, right? So now we have like that, and there's a charge. Okay. So, which of the following molecules are nonlinear? Right? That's trigonal planar. Electronic geometry. Molecular geometry is bent. So this one is nonlinear. That's a nonlinear. Check that off. All right, what's the next one? C2H2. All right, so this is 2 times 4 is 8, and that's 2 is 10 electrons. Carbon, carbon, hydrogen, hydrogen. 2, 4, 6. 4 electrons. Okay. How do we make an octet for each carbon? Make a bond out of that one, make a bond out of this one. Because that's 2, 4, and it's 6, 8. Yeah, okay, so now we have this one. Right? That's acetylene. And this is a linear molecule. Right? So that's not it. Can't use that one. We need a non-linear. How about N3 minus? Okay. 5 times 3 is 15 plus 1 is 16 electrons. Got that? 3 times 5 is 15 plus 1 is 16. Okay, got N. Okay, minus 4 is 12. 1, 2, 2, 4. 6, 8, 10. So all the peripheral nitrogens have their octets. And we have 2 extras that go in the center. Okay. Now, this one does not have its octet. So we need to take 2 from one side of the other. And that makes there we go. So that's your Lewis dot structure. Now, the central atom, this one, you got 3 groups. Trigonal planar. Cover up the electrons. Now you have a bent molecule. So this one's bent. It's excuse me. Yeah, we're looking for the nonlinears, aren't we? Okay. So this one is nonlinear. All right. How about, let's see, what do we got next? HCN. We did this one before. That's linear, right? Can't use it. We've done this one before. That's linear. Can't use that one. H2O2. Uh, 6, 12, 14. 14 electrons. 2, 4, 6. 8 electrons. 2, 4, 6, 8. Okay. Now we have 2 centers, 2 central atoms. This one with 4 groups, tetrahedral, right? Electronic structure. Cover up the 2 lone pairs, and you got a bent molecule. It's bent around oxygen, and it's bent again around that oxygen because they're both the same structures, right? So this one is bent. Oh, nonlinear. I always do that. So this one. So we have 3. NO2 minus, nonlinear. Wait a minute. It says that this one and that one are correct. And this one is linear. Let's do that one again. I may have made a mistake. So N3 minus, right? Nitrogen is up 5. Okay, so 15, 16 electrons. N minus 4 is 12. So we got 2, 4, 6, 8. Oh, you know what I did wrong? 3 times 5. No, I did that wrong. 3 times 5 is 15, 16 electrons. No, that's right. 2, 4, 12 electrons. 2, 4, 6, 8, 10, 12. There we go. Yeah. Remember last time I put a lone pair here, it wasn't supposed to be there. This is 2, 4, 6, 8, 10, 12, 14, 16. Okay, now we're good. Now, in order to make an octet around this one, we need, let's see, there and there. So now we have N minus with 2 pair here and 2 pair there. That is linear. Yeah, that's linear. So we can't use that one. These are this one. This one and, oh, I must have erased it. Yeah, I did. I erased H2O2. H2O2. There. Nonlinear. That's nonlinear. That's nonlinear. Those are the only 2. So the answer is C. All right, let's see. 38 coming up. and 39. That was about to run out of ink. I'm going to use this one. 38. The molecular structure of BRF6 plus. Or if they show up good on it. Does that? Yeah, it looks like it's doing okay. All right, I hope it does. What's the molecular structure? Remember, we have to do the electronic structure first, then the molecular structure. Does that perfectly not show with this weird lighting? Okay, so we got to do the Lewis dot structure. There's 7 halogens, which is 7 times 7 is 49, right? 49. But we've got a plus charge, which means we lost an electron. 48 electrons. So bromine is going to be in the middle. 1, 2, 3, 4, 5, 6 fluorines. Okay. 2, 4, 6, 8, 10, 12. Which is 36. 6 around each fluorine times 6 is 36. So we used them all up. And there's a plus charge. Now, we don't have any lone pairs around bromine, which means our structure, our electronic structure and our molecular structure are the same. With 6 groups around bromine, that's octahedral. So that's why the answer is C. Very nice. What type of structure does the following molecule have? Xenon, oxygen, fluoride. Xenon, fluoride. Okay. This has 8, that's 6. 2 times 7 is 14, so that's 28 electrons. Now, which one's going to be in the center? In this case, if you've got an inert gas that's been forced into a molecular formula or a bonding, in this case, xenon will be in the center. Like that. So that's 6 electrons used up, 22. Two, 4, 6, 8, 10, 12. That's 10 electrons, right? Left over. 2, 4, 6. That's 6. That's 4 electrons. 2 pair right there. Okay. So the electronic structure here is 1, 2, 3, 4, 5. Electronic is trigonal bipyramid. Okay. But the molecular structure, I have to draw a map out for this one. Xenon in the center, and then we're going to have like that. All right, remember where the lone pairs go. The lone pairs usually go on the triangle for this geometry. So we would have a lone pair here and a lone pair here, and that would put oxygen back here and fluorine there and fluorine there. So what does that look like when you say turn it on its side? You've got a bond here and then bonds there. That is T-shaped. And our selection is C. Okay? All right, 39. Let's see what's next. 44. Select the correct molecular structure for SiH4. This one should be really simple. How many valence electrons are for silicon? Silicon's in the same family as carbon, so it has 4. And this has 4. So that's 8 electrons total. Silicon, 1, 2, 3, 4. 2, 4, 6, 8. Used them all up. That's a tetrahedron. Which is B. Okay. This has a special name. This is called silane. If this were carbon, it would be methane. So we just take SiL from the silicon, plug it in there, and instead of methane, it's silane. All right, 44. Let's see, too far. 46. Select the correct molecular structure for BeCl2. Okay, beryllium. Beryllium is 2 over from the left, which means it has 2 valence electrons. Halogens have 7 each, so that's 14. 16 electrons. Okay, beryllium in the center because it's to the left. It's the more metallic. Fluorine here. So that's 4, which is 12, right? 2, 4, 6, 8, 10, 12. That's it. Beryllium is deficient. It has less than an octet. But it's real. It does exist. And 2 groups around the central atom means linear. All right, so that's A. All right. 46, 47, 48, I think is one. 49. Yeah, we can squeeze 49 in there, I think. Roll a little bit. There we go. 48, 49. All right. The molecule XEF2, in the molecule XEF2, xenon difluoride. How many pairs of electrons surround xenon, and what's the molecular geometry? Okay. That's 8. These 2 are 14, which is 22 electrons. Xenon, then fluorine, and fluorine, minus 4, which is 18. And 2, 4, 6, 8, 10, 12. Minus 12 is 6. So that means 3 pairs. Okay? 3 pairs of electrons surround. Oh, that's an easy one. Right? Our selection C says 3 pairs, and none of the others say 3 pairs. And it tells us that geometry should be linear. And in fact, it is. Because this is 5 groups makes a trigonal bipyramid. But all of those lone pair electrons are on the triangle. And the fluorines are at the apex. So that is a linear molecule with 3 pair of electrons. Let's see, that would be C. All right, 49. Choose the member of each set that best matches the label. Oh, okay. Of beryllium and barium. Beryllium and barium. Which is the more metallic? What we mean by more metallic, several things could be used. The more metallic has lower electronegativity. In fact, that's the best way to think of it. So the lower electronegativity, since beryllium is up toward the top and barium is toward the bottom, barium would be the more electronegative. I mean, the least electronegative, it would be the more metallic. Metallic means a desire, strong desire to give up electrons. So if it has a low electronegativity, it's more likely to give up its electrons. So barium would be the first one, more metallic. N2O versus MgO, more covalent. This one's simple. That's a metal, that's a non-metal. This is a non-metal, non-metal. That's more covalent. And highest electronegativity, oxygen, sulfur, bromine. The highest electronegativity is the one that's furthest to the right and up in the periodic table. And that would be bromine. Oh, wait a minute. Highest electronegativity. No, oxygen. Bromine is below oxygen. That's the more electronegative. In fact, oxygen is right next door to fluorine. So it'd be barium, nitrous oxide, and oxygen. Barium, nitrous oxide, and oxygen is E. All right. Then I'll do 50. This is going to take a little work. Use bond energies to give below to calculate the enthalpy change for the reaction. Oh, this is not going to be too bad. So here's the reaction, the balanced equation. HCN plus 2H2 yields CH3NH2. Remember, the calculation is delta H equals the sum of the bond energies for the reactants minus the sum of the bond energies for the products. Okay. In order to know which bond energies to use, you've got to know something about the structure of the molecule. Right? And we know that this one, we've drawn this one before. HCN. This one, of course, is HH. This one uses that organic chemistry trick I told you before. These hydrogens belong to that carbon. And this is bound to the nitrogen, and this one has a hydrogen there and a hydrogen there. That gives this an octet, and that has an octet too. Now, in order to prove this one, you'll have to draw the Lewis dot structure. Right? I already know it, so I'm not going to take time to draw the structure to prove the structure. That's it. Okay. So the bond energies here are a hydrogen carbon 413 times 1 plus a carbon nitrogen triple bond 891. Okay, plus 2 times hydrogens 432 each. Okay, now we subtract everything inside this one. We have 1, 2, 3 carbon hydrogens, 413. Then we have a carbon nitrogen, 305. Then we have 2 nitrogen hydrogens, 391. There we go. So if you do that math, you should come up with minus 158 kilojoules. In the interest of time, I'm not going to go through the math. That's how you set it up. Each one of those bonds has an energy, and you have to use the coefficient of, and the coefficient in this case is how many of the bonds are there? In this case, there were 2 of these. In this case, there were 1 molecule, but there were 3 bonds. 3 bonds. 1 bond here, 2 bonds there. Okay, that's essential. All right, that was 50. $51. This is going to take some doing. Okay, question is, given this following information, each of those, where's my pointer? Well, my pointer doesn't show up too well anyway. Each one of these reactions, lithium solid to lithium gas, is 166 kilojoules per mole. And that's a positive value. It means you got to put energy into that solid to make it a gas. That makes sense. And on down the line, bond energy is the given value. Then we have ionization energy, electron affinity, lattice energy, and bond energy of hydrogen. Okay, so since we're given all this information and we want to calculate the enthalpy for this equation where lithium solid is reacted with hydrogen bromide gas to yield hydrogen gas and lithium bromide solid, the best way to approach this one is with Hess's law. In other words, we've got to combine those equations in such a way that we get this target equation. Separate that. And 2 lithium bromide solid. Okay. Let's see. Lithium to lithium gas. Here's lithium solid. Okay. So we need 2 of them. We need 2 lithium solids yields 2 lithium gas. And the enthalpy for this one will be twice the listed one. So that would be delta H under here. This is going to be 12, 1, 12, 13, and 1 and 2 is 3. Okay, that's kilojoules. All right, so we got this one taken care of. Do we have anything with HBr in it? Yep. HBr gas, the next one. We need 2 of them. And they're on the right side of the equation, so 2 HBr gas yields 2 H gas plus 2 Br gas. Okay, we need twice that number. So twice 363 is 6, 12, 7. Okay, so we got this one. Now we need hydrogen gas. Who's got hydrogen gas? This one right here. But it's on the wrong side. It needs to be on the other side, which means we need to change the sign on the enthalpy. And we don't have to multiply. Right? It's got however many we need. Hydrogen gas. And on this side is 2H gas. We just need to change the sign from 432 to minus 432. Okay, that takes care of this one. Okay. Let's see, let me keep track of these two. That one, this one, that one, and this one, that one. Okay. Now, lithium bromide. Lithium bromide, we use for lattice energy. And there are 2 lithium bromides, so we need to double the value. 2 lithium pluses plus 2 bromide minuses yields. Let me make that a little shorter. Lithium bromide, 2 of them, solid. Okay, so now we need 2 times that value, which is minus 809. We have minus 918. 2 times 9 is 18, 2 times 0, and then 1, and then 2 times that is 16. So 1618 kilojoules negative. Okay, that makes sense. I mean, lattice energy is huge, and that's a huge exothermic reaction. Okay, so we got this one and that one. Okay. Now what we've got to do, since we've got, it's kind of hard to see that, isn't it? We've got this one done, this one done, this one, and this one. Now, we've got to get rid of these other terms that don't exist up here. So that lithium gas, where's lithium gas? The third one down. Lithium gas, and we need 2 of them. And we need the lithium gas to be on this side so that it'll cancel that one. So 2 lithium gas yields 2 lithium plus gas plus 2 electrons, right? Ionization energy. It's on the right side, but we need 2 of them. So we need 2 times 520. So that's plus 1040. That's a plus and that's a plus. Okay, so that gets rid of this one. And this one. Right there. Okay. What else we got? Oh. We got these to cancel. And that's a bromine gas. So we need bromine. We got to get rid of bromine gas. So we need a bromine on this side. And there it is, the fourth one down. But we need two of them. Two bromine gas yields. Oh, excuse me. 2 electrons. This is electron affinity for bromine. There we go. So we didn't have to flip it. So we just need to multiply minus 325 times 2 minus 650. Okay. Now what that does for us, gets rid of the electrons and it gets rid of the bromine gas and it gets rid left side, right side. It gets rid of the bromide ion. Now let's see. Done, 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 done. Add them up. Add them up. We should end up with minus 602 kilojoules, which is B. Okay, that was a lot of work, which is why when you're using Hess's equation, you got to be extremely careful and methodical about it. All right, 52. Scroll it just a little bit. All right. This one takes a little bit more finesse. First of all, we've listed these enthalpies. And from that information, we want to determine the lattice energy for rubidium chloride. All right. Well, our target equation has to be the lattice energy equation for rubidium chloride. So we write that up there. We got to know rubidium. Where does it come from? It's an alkali metal. So 1 rubidium, 1 chlorine. The lattice energy for rubidium chloride. So we're going to end up with rubidium chloride solid. And the way you get to that through lattice energy is rubidium plus gas plus chloride gas. That's our target equation. Okay? And we want to know what is the lattice energy. What's the value of the enthalpy for that reaction? First thing we're going to do is deal with this one right here. Where do we have that one? We have it in the ionization energy of rubidium. Remember, rubidium ionization energy is 397.5 kilojoules. But the ionization energy will put the ion on the wrong side. So we have to flip it. And instead, put the ion on this side. With its electron. There we go. And now we have to change the sign. Minus 397.5. 0.5 kilojoules. All right, that takes care of this one. Now we're going to deal with the chloride ion. Right? Chloride ion on this side. Where do we have the chloride ion? Well, in the electron affinity, we have a chloride ion that's formed on that side. As we add, if we add an electron to this one, we get that one, right? So we're going to flip that one also and put the chloride on this side. That means the chloride ion as a gas yields chlorine gas plus the electron. And now we have to flip the value from minus 332 to plus 332. Okay. That takes care of this one. There. Now we're going to deal with rubidium chloride. Right? Rubidium chloride is heats of formation. The enthalpy of formation is the second one from the bottom. That's going to, as is going to put rubidium chloride solid on this side, and on the other side, we're going to have rubidium solid plus 1/2 chlorine gas. And that value is going to be minus 431 kilojoules. We didn't have to change that one at all. So that gives us this one right here. Now what we have left over are these other things that we need to get rid of. Well, the electrons are already gone. Right side, left side, electrons are gone. What I want to get rid of next is the rubidium gas. And if I put the rubidium gas on this side, that top one, rubidium gas, is on the right side. So we got to put it on the left side and change the sign on the enthalpy. So if we put rubidium gas here to rubidium solid, that's the deposition energy, which would be minus 85.8 kilojoules. Okay, so what does that do for us? That gets rid of this one right there, and it gets rid of this one, that one. Okay, what else do we have left? We have bond energy of chlorine. So where do we have chlorine? I always leave that out. That's 2. We have chlorine on this side, right? So we need chlorine gas on this side. Yeah. Bond energy is going to put Cl. Well, actually, we have to flip it because bond energy is going to put chlorine gas on this side and make chlorine atoms on that side. So we're going to change the sign. This is gas, and this would be 2 chlorine atoms. Right? But we only need 1/2, right? If we're going to cancel this one with that one, we only need 1/2. So we have flipped the equation, and we take 1/2 of it. So the bond energy, the middle one, BeCl2, we need 1/2 of that and change the sign. So it's a negative 113 kilojoules. What does that do for us? Well, now this is only one chlorine. One chlorine. And this is 1/2 of a chlorine. So that gives that one, there. Okay, so we cancel. Got that one up here. Cancel. Okay, we've got everything canceled. Now, we add that together, and we should get minus 695 kilojoules. Okay? That one's a lot of work. That looks like a prospect for an extra credit. That was 52. Okay, what's next? 52. 53. All right. Explain. In spite of the large electron negativity differences between bonded atoms, beryllium and chlorine, in this molecule, large electron negativity difference, it has no dipole. While this one, this is non-polar. This one is polar. All right. Explain. We drew beryllium chloride early, and it looked like this. I think we drew it earlier. Right. 2, 4, 6, 8, 16. So that's 2 and 14 is 16. That's a linear molecule. So this dipole cancels that dipole. That's why this is nonpolar. Whereas this one has, let's see, 14 plus 6 is 20 electrons. Sulfur, chlorine. So that's 2, 4, 6, 8, 16. 4 electrons. There. This one is going to be tetrahedral. Electronic geometry. And bent. Molecular geometry. All right. So that means that the dipoles here and here are additive. That means this one is, since it's a bent molecule, it is polar. Right. That explains the polarity. It's not the polarity, just the polarity of the bonds, it's the geometry that matters. All right, 53, 54. For ICl4 minus, ICl4 minus, draw the Lewis structure, okay? Both halogens, so 5 times 7 is 35, plus 1 equals 36 electrons. Okay. Iodine's in the center. Chlorines. That's 2, 4, 6, 8. That's 28. 2, 4, 6. 2, 4, 6. 6. 6. So 4 times 6 is 24. There's 4 electrons. They have to go here on the iodine. So what does that make the electronic geometry? 1, 2, 3, 4, 5, 6 groups is octahedral. Electronic. So that means we've got a square, and then we've got iodine in the middle. And we've got something up here and something down here. Right? So what do we have up here? Well, in octahedral arrangements, if you have lone pair electrons, they tend to go out here. Like that. So that means chlorine's here, chlorine's here, chlorine's here, chlorine's here. All right. Now, the Lewis dot structure, you could either say this one, that would be valid, with a negative. Without that bracket and the negative sign, that's not correct. And the geometry then, the shape of the molecule is square planar. That's the molecular geometry. Square planar. Okay? Now, is it polar or non-polar? Well, chlorine is a little more electronegative than iodine. But all of those equal in magnitude, polarities, the dipoles. These dipoles are all equal in magnitude, but they're pointing to the apex or the corners of a square. So they cancel each other out. This is a non-polar molecule. And if you're worried about these lone pairs, they're opposite one another. They cancel each other out too. This is a non-polar molecule. All right. 54. That's it.